Today we discuss about eigenvalues and eigenvectors. Eigenvalues and eigenvectors are fundamental concepts in linear algebra. An eigenvector of a square matrix A is a non-zero vector V such that when A is multiplied by the vector V, the result is a scalar multiple of V. This scalar is known as eigenvalue lambda. Let us consider the linear transformation y is equal to ax. Now replace the matrix A by any number, say lambda. Then 1 becomes y is equal to lambda x. Now we are replacing this A matrix A by any particular number lambda. Now since the left hand side of both the equation 1 and 2 both are same, so similarly the right hand side will be also same. From 1 and 2 we have ax is equal to lambda x. Now let us transpose this right hand side to the left hand side. We have ax minus lambda x equal to 0. Now this lambda can be written as lambda into I, where I is identity matrix. So instead of writing x, because we know that if we multiply any matrix to its identity matrix, we get the same matrix like Ix is equal to x. Therefore, instead of lambda, we are writing lambda I. Now if we take x outside from these two things, we are getting a minus lambda I, and x we have taken outside. This is a metric equation on x. Keys of eigenvalues and eigenvectors. The first thing is the characteristic matrix. The matrix A minus lambda I is called eigenmatrix, or characteristic matrix, or it is also called latent matrix. Next, second thing is the characteristic or eigendeterminant. If we take the determinant of this characteristic matrix, determinant of lambda I is called eigendeterminant or characteristic determinant or latent determinant. Third one is called characteristic polynomial. The polynomial a minus lambda I, determinant of a minus lambda I in lambda, is called polynomial or characteristic polynomial or latent polynomial. If we simplify this determinant a minus lambda I, we get a polynomial equation in lambda. The fourth one is called characteristic equation. The equation a minus lambda I, which is equal to 0 in lambda, is called eigenequation or characteristic equation or latent equation. The degree of the characteristic equation of a matrix is equal to the order of that matrix. So suppose if the order of this matrix is 2, so the degree of the equation will be 2, and so on. The next thing is the characteristic value or root. The values of lambda, which is obtained from the polynomial equation a determinant of a minus lambda I equal to 0, are called eigenvalues or characteristic values or latent values, or sometimes it is also called proper values. So now this determinant of a minus lambda I equal to 0, this is the polynomial or equation in lambda. If we simplify it, definitely we get the value of lambda and that values of lambdas are called eigenvalues. Next thing is the spectrum of a matrix. The set of all characteristic roots of a matrix is called the spectrum of matrix. So now, if we are able to find out the characteristic root of any given matrix, so the set of all characteristic roots of a matrix is called the spectrum of the given matrix. Eigenvector. The values of X are called eigenvectors, are characteristic vectors, are latent vectors corresponding to the eigenvalue lambda. So if we have given the values of lambda, then we are able to get what are the values of eigenvectors. The very important point over here, any non-zero vector X is said to be characteristic vector of a matrix A if there exists a number lambda such that AX is equal to lambda X. So here the value of X is called characteristic vector or eigenvector. Now let us check what is the history of eigenvalues and eigenvector. So the first point is the concept of eigenvalues and eigenvectors has its roots in the work of 18th century mathematicians like Euler and Lagrange. In the 19th century, the term eigenvalue was introduced by Augustin Louis Cauchy. Contribution from William Rowan Hamiltonian and Arthur Kelly further developed these concepts. Over the 20th century, eigenvalues and eigenvectors become central to various branches of mathematics and science, including quantum mechanics, stability analysis, and numerical methods. Let us discuss about some properties of eigenvalues. The first property is trace of a matrix. The sum of the entries of the main diagonal of a matrix is called the trace of a matrix. When we take the example, we will discuss all these things in detail. So what is the trace of a matrix? This is nothing but the what are the entries? Sum of all the entries of the main diagonal of a matrix is called trace of a matrix. That is, if we have given a matrix A11, A12, A13, and so on, n by n matrix is given. So what is the diagonal element? A11 plus A22 plus A33 plus An. So this is called trace of a matrix. For example, if I have given the matrix 1, 2, 3, 0, 1, 3, 4, 5, 6. So what is the trace of this matrix? It is nothing but what is the sum of the main diagonals. So now here 1 plus 6, which is equal to 8. This is called the trace of the given matrix. Next, the sum of the eigenvalues of a matrix is the sum of the elements of the principal diagonal. So suppose if we have given a matrix A, which has 3 eigenvalues, so that sum of that eigenvalues will be equal to the trace of that matrix. This is called the sum of the eigenvalues of a matrix is the sum of the elements of the principal diagonal. So what is that? The sum of elements of the principal diagonal is nothing but trace of a matrix. So trace of A, which is equal to A11 plus A22 plus A33 up to AAN, which is equal to lambda 1 plus lambda 2 plus lambda 3 up to lambda n. Suppose the order of this matrix A is n, then it has n number of eigenvalues, lambda 1, lambda 2, lambda 3 up to lambda n, and it has n number of diagonal elements. So now the sum of all diagonal elements, which is equal to the sum of the eigenvalues. The eigenvalues of an upper or lower or diagonal matrix are the elements on its main diagonal. What it means? It means that suppose we have given this is the matrix 0, 0, 0, 5. So now this is what it is called, the diagonal matrix. What is diagonal matrix? A matrix in which except the diagonal elements, all elements are 0. So now here, this is diagonal element. So if you want to find out the eigenvalue of this diagonal matrix, the diagonal elements 1, 2, and 5, these are the eigenvalues. Similarly, instead of if we are taking the diagonal matrix or upper triangular matrix or lower triangular matrix, so in this all these three cases, the diagonal elements are the eigenvalues of the given matrix. The product of the eigenvalues of a matrix is equal to the determinant of the matrix. So now, if we are able to find out the eigenvalues of the given matrix, we have to just multiply the eigenvalues of the given matrix. That is nothing but the determinant of the given matrix A. Now, so using these two properties, trace of A, which is equal to the sum of eigenvalues, and multiplication of eigenvalues, which is equal to the determinant of A, these two properties can be very much useful to check our answer, that our answer is correct or not. The property number 5, if lambda 1, lambda 2, lambda 3 up to lambda n are eigenvalues of the matrix A, then 1 upon lambda 1 up into 1 upon lambda 1, 1 upon lambda 2, 1 upon lambda 3 up to 1 upon lambda n are eigenvalues of A inverse. Now, if we have given a matrix A and the eigenvalues of that matrix are given, and if we have the its inverse matrix, then we are able to say that what are the eigenvalues of the inverse of the given matrix. It is nothing but we have to just take the inverse of each and every eigenvalues. Property number 6, if lambda 1, lambda 2, lambda 3, lambda n are eigenvalues of A, then k lambda 1, k lambda 2, k times of lambda 3 up to k times of lambda n are the eigenvalues of the matrix K A, K times of A. Seventh property, the eigenvalues of A and its transpose, A transpose, are same. So if we have we have given a matrix A, if we have eigenvalues of A, then we are able to say that what is the eigenvalues of transpose of A. It will be the same. Both matrices A or A transpose both have the same eigenvalues. Eighth property, if lambda 1, lambda 2, lambda 3 up to lambda n are eigenvalues of A, then lambda 1 to the power m, lambda to the 2 to the power m up to lambda n to the power m are eigenvalues of A to the power m. So this m is the any positive integer. Property number 9, if lambda 1, lambda 2, lambda 3 up to lambda n are eigenvalues of A, then lambda 1 minus k, lambda 2 minus k, lambda 3 minus k up to lambda n minus k are eigenvalues of A minus ki. Property number 10, the eigenvalues of a symmetric matrix are real. Eigenvalues of a symmetric matrix are real. Properties of eigenvectors. Now, we have already seen what are the properties of eigenvalues. Let us take some properties of eigenvectors. First property, eigenvector of a matrix corresponding to eigenvalue lambda is not unique. What it means? It means that for one eigenvalues, we are able to get infinitely many eigenvectors. The second property is let lambda 1, lambda 2, lambda 3 up to lambda n be distinct eigenvalues of A, then corresponding eigenvectors x1, x2, x3 up to xn are linearly independent. This is very important property. If all these eigenvalues lambda 1, lambda 2, lambda 3 up to lambda n are distinct, then definitely the corresponding eigenvectors x1, x2, x3 up to xn, they all are linearly independent. Property number 3, it may or may not be possible to get linearly independent eigenvectors corresponding to the repeated roots. So if the roots are repeated, means lambda 1, lambda 2, lambda 3 up to lambda n, not all are different, then at that time we can get the possible linearly independent or linearly dependent eigenvectors. An n by n matrix has at most n linearly independent eigenvectors. Property number 5, eigenvector of a square matrix cannot correspond to two distinct eigenvalues. Property number 6, orthogonal eigenvectors. Two eigenvectors x1 and x2 are said to be orthogonal if x1 into x2 transpose, which is equal to 0. So this is called orthogonal eigenvectors. Property number 7, eigenvectors of a symmetric matrix corresponding to different eigenvalues are orthogonal. And the last property, corresponding to zero eigenvalue, eigenvectors will not be zero. So if it is possible that the lambda's values may be zero, the value of lambda may be zero, but corresponding to zero eigenvalue, it, it should not be vector, zero vector means vector should not be zero. Thank you.